Hello. What's up? Okay, so today I'm going to be talking about I came up with a Syscall hooking technique like 2 weeks ago, and I kind of wrote it up, just a novel Syscall hooking technique. I'm going to talk about that. So before we start with the novel Syscall hooking technique, let's talk about the non-novel Syscall hooking technique, otherwise known as ptrace. I also have like no slides today because who needs slides? So ptrace is typically the way you basically debug or hook anything. So when you ptrace something, so for example, let's say you're using like GDB or LLDB on a debugger. Typically, what it'll do is it'll essentially, using ptrace, it'll attach to another process, and using ptrace, you're able to manipulate a foreign process. So for example, you're able to read and write data and code. You're able to read data and code, write data and code, get the registers, set the registers of a foreign process. The other interesting thing you're able to do is get syscall info. That is how you kind of you can hook syscalls using this. I forget exactly how. Ptrace is a really confusing system call. My point is, using ptrace, you're able to hook a system call and basically look at the arguments to that system call and understand what's going on. So I guess before I even talk about, I guess a few things about system call hooking. So what is a system call? A system call basically is basically a call to the kernel. So there's a lot of operations, in fact most operations on a computer, a user program can't do alone. Instead it needs to make a call to the kernel. So for example, let's say you want to read a file, right? If you want to read a file, you need to you typically call the read syscall or fread or whatever. Point is, they all eventually hit the read syscall. The reason you need to call the read syscall is because when you're reading from a file, you need to read from the disk, and a user program is not directly able to interact with a disk. Like it would instead need to essentially hit the driver, and the driver is in the kernel. So you need to make a system call to the kernel, and the kernel will handle it, and it'll pass back the result. Now, why do you typically want to? Why should you care about tracing syscalls? Tracing syscalls is powerful because tracing and manipulating syscalls rather is powerful because if you're able to manipulate system calls, you're basically able to see exactly what a program is doing. Like exactly how it's interacting with system resources. So for example, if it's opening a socket, if you can hook the socket system call, you can see exactly when it's opening a socket, exactly when it's sending data over the network, exactly when it's reading and writing to a file. You can see all that information just by hooking the system calls. So in that sense, if you're able to hook system calls, you have a very powerful primitive when it comes to reverse engineering certain pieces of software. But ptrace is very, very well known, and it is easy as hell to hook. Well, it's easy as hell to detect. There's many things like ptrace, trace me. There's a bunch of techniques that exist these days to detect if a process is currently being traced by another process. So it is nice to have kind of a different technique that people don't know about, and it's harder to detect. So that's kind of what I came up with. So the technique that I specifically came up with is using a thing called BPF. There it is. So this is the code. So what is BPF? BPF is kind of an assembly language that exists within the kernel. It's not specifically meant for the kernel, but it exists within the kernel. It allows you to basically build a program, and this program is built with BPF instructions, and those BPF instructions, upon a certain event occurring in the kernel, those BPF instructions will run and that BPF program will run. So basically it allows you to hook certain things. BPF is used throughout the kernel for a variety of purposes. The two common ones are eBPF, which is primarily used for networking operations. So for example, there's I think Cloudflare has a really good article on how they use eBPF. But basically, like when you receive a packet, you can basically run this eBPF program on the packet to decide what to do with the packet. So it's basically net filter on crack in that sense. eBPF also has a bunch of other purposes like kprobes, and there's all kinds of things you do with eBPF. In fact, the list, I think it's BPF types. I think that's the header file. It's that's the list of things you can do. Those are all the programs. You can see like the C group, SKB, I don't even know what that is. Sockets. can hook all kinds of stuff with the BPF. It's very nice. Trace points, K-probes, perf events, stuff like that. The other thing that's really common with BPF is Seccomp BPF. Seccomp BPF is another way to use BPF, and Seccomp BPF basically allows you to run a program. I guess if I can look up Seccomp. Seccomp BPF allows you to basically run your BPF program when a syscall occurs. And using that, in that BPF program, you can observe what the actual arguments are, and you can basically decide based on those arguments whether to reject or accept or, in this case, actually trap a syscall. So, for example, let's say Seccomp is primarily a sandboxing technique. So let's say you don't want a program to open specifically Unix sockets, right? What you could do is you create a Seccomp program to hook the Unix the socket syscall. You could look at I think it's the AF. What is it? I don't even remember anymore. You can look at the family argument, and you can say, okay, you can check if it's the AF Unix family, and if it is the AF Unix family, you can deny the syscall, and that would basically kill the program. So in that sense, it provides a very, very powerful technique to easily sandbox programs and prevent them. And because it's a program, it's not like a set of rules. You can very, very easily control exactly what it's doing, exactly what it rejects, exactly what it accepts. So that's kind of Seccomp. Seccomp is a technique used here. So from Seccomp, you have kind of three options. Actually, four options for what you're allowed to do. These are actually you have a bunch of options. So the most common that you have is, well, the Seccomp ret allow. So this is what you return from your Seccomp program is basically what the kernel does. You have Seccomp ret allow, which just allows it. Seccomp ret log, which logs it. Seccomp ret trace, I forget what trace. Seccomp ret trace will interact with a ptrace process. User notif, I think this is like a notification. Error, you can basically pass back an error. Ret trap, which is what we use, I'll get back to that. Kill thread, we'll just kill the thread. Kill process, we'll just kill the entire process. Pretty simple in terms of what options you have. The one we care about is ret trap. Ret trap is a funny one. So ret trap will basically allow you, when you return ret trap, it'll deliver what's called a SIG-sys. It'll deliver the SIG-sys signal to the process. And you can actually catch the SIG-sys. You can actually catch the SIG-sys system call. I mean, the SIG-sys signal. So basically, what we do, on principle, the idea is that we basically create a Seccomp program to basically filter a certain number of syscalls. So let's say we want to trace the socket system call, right? Basically what we'll do is we'll create a Seccomp program that if we see the socket system call, we'll just return Seccomp ret trap. And then on our process side, we'll basically create a SIG-sys handler, and that SIG-sys handler will then handle the hooking of the system call. And we're through like signal handling and through the things the signal provides, we're able to see basically everything ptrace can see. We can see the system call number because it actually gives the system call number here. We can see what else can we see? We can see the arguments as well. I guess that's really all that matters. We see the arguments and the system call itself. So that's Seccomp ret trap. Basically, we throw in a signal, and basically, we can catch that signal, and in that signal handler, we're able to basically manipulate and read what the system call is doing. Now, there's kind of a few issues here with Seccomp ret trap that we have to work around. One, with Seccomp ret trap, it doesn't run the system call, which is good for us because we're able to manipulate the arguments of the system call before it runs it. The second thing is that it'll basically skip the system call. You kind of have a weird issue where if you try to rerun the system call, what'll happen is that it'll basically trigger the Seccomp program again, and it'll ret trap again. So basically, your main issue is here that you can never run. Is that under the kind of our architecture, you can basically never run a system call. I guess a system call of a specific type, because every time it'll ret trap. So there's no way to actually run the system call. So for example, let's say you hook the socket system call, right? In our seccomp program, we'll return seccomp ret trap, and then seccomp ret trap will take us to our SysSys handler. In our SysSys handler, if we try to rerun the system call, it'll ret trap again, and that ret trap will take us back to our SysSys handler. So basically, we have an infinite loop that we can't really break out of. But there is a solution to this, and it has to do with how seccomp kind of transfers between threads and processes. So yeah. So first thing, I guess, that we kind of do is, what's going on here? Let's see. Is this the? Yeah. Okay. That's handler. What did we set? Trap handlers here. Okay. So in terms of how it works, let me first talk about the BPF program. So basically, what we allow is we've taken this is C++, by the way. We've taken a vector, which is basically, if you're not familiar with C++, a vector is basically just an array list. We take an array list of system call numbers. This is the constructor for our BPF hook object. We can't have too many, otherwise it's not going to work. It's like, you can have, I believe, 253 because of the size of a seccomp program. Basically what we do, it's a pretty simple thing. In our first instruction, we just grab the grab the system call number from the seccomp data. Then we basically just create a bunch of instructions for every system call thing. So basically, all we do is we just what do we do here? We just compare. We compare the system call number with every system call number that we are trying to hook. So I guess syscall numbers are the system call numbers that we're trying to hook. We compare it with every system call number we're trying to hook. If it matches, we then jump to the trap, this trap instruction. This just returns seccomp ret trap, and if no match occurs, then it eventually falls through into the seccomp ret allow. So on principle, it's actually a pretty simple program. Basically, all we're doing is it's basically just a series of if statements. If it's every single one of these numbers, then I guess if it's any of the numbers, then return ret trap. If it's not any of the numbers, then just allow it, right? So basically, if we're trying to hook it, ret trap. If we're not, then just return allow. This is how we create the program. It's not too bad. We have instructions, total instructions. Yeah. So we also have, this is where we hook. That's our hook right there. That's how you hook stuff. Let me zoom in a little bit. That's how you hook stuff. You just sig sys, and this is your sig action. That's our handler. Is our trap handler right here. Now, back to our original problem. Back to our problem about why we can't. How do we get around this issue of hitting that infinite loop, where we can basically never run the syscall? The way we get around it is abusing how Linux transfers seccomp programs. Now, whenever you fork or create a new thread whenever you fork or create a new thread, the new process inherits the old process's seccomp filters, which is funny, right? Because I mean, it makes sense because you don't want a program to fork and then suddenly be able to escape the sandbox, right? Which makes sense, because otherwise, if you set a certain sandbox on a certain process, and an attacker gets into that process, then they would just be able to fork and then just break out of the sandbox, which is stupid. Which is why, one, you can never remove a you can never remove a seccomp filter, because again that would just be trivial to break out of the sandbox. Two, you cannot create a new process to break out of the seccomp filter. Now, I guess let me talk about where that thing is transferred real quick. It's actually very simple code. All it is it's run in the whenever you fork, there's a copy. It just basically just runs this copy process function in the kernel. This copies literally everything about the program. You see this kind of just like this series of if statements here. The place it specifically copies it is where does it copy it? It's funny, it's called copy seccomp is what it is. Seccomp. Just copy the seccomp. All it does is literally just does that literally just takes the current process Seccomp and puts it in a new process Seccomp. Now, the important thing is that this code also runs on threads, right? This code is also running on threads. It only copies the current process Seccomp. It doesn't actually, it's not going to inherit any new process. So I guess if after the fork or after a thread is created, if the new thread creates a new Seccomp, or a new process creates a new Seccomp filter, the old thread is not going to inherit it, which is good. So basically what we do is really simple. All we do is we create basically a handler thread. We create a second thread. That thread is essentially just a worker thread. And that worker thread will basically just be running syscalls that are hooked by this trap handler. So yeah, I mean that's kind of the idea. So we create a new thread. This is our worker thread. Then right after the worker thread is created, we just insert it. We create our we essentially insert and start our Seccomp filter. So, and because we've already created this new thread, and because of this code right here, this thread will not inherit this Seccomp filter program. So basically, we have a nice situation where we have thread 1, which is currently hooking all the syscalls, and thread 2, which is not subject to any kind of sandbox. So that's actually a very nice situation to be in. What else? So basically, what we do here is we have this, and I guess the other key thing is threads are nice, right? Threads are good to have here because threads basically share every other resource, right? So for example, let's say we have the write system call, right? The way the write system call works is the write system call, the second argument is a buffer. It's a pointer to a buffer, and that buffer is basically the data that you're writing to the file. In this case, because it's a thread and not a new process, those two threads share the same memory space. Therefore, thread 2, our worker thread, can actually access the buffer that thread 1 was trying to write, right? Because keep in mind they share the same memory space. So in that sense, it's also very good because we don't need to worry about we don't have to worry about like losing resources and stuff. Yeah. What else? I mean, the way the thread thing works is pretty simple. The trap handler basically just takes the system call, creates this system call request object, which basically just pulls system call and all the arguments, and then all it does is it inserts into a queue and then waits until it's done. This thread handler, pretty simple. All it does is pulls shit off the queue, runs the system call, and then just notifies the owner when it's done. That's it. Just a nice little, just like a producer-consumer queue thing. Probably should use like a channel or something, but I don't know. I didn't really care that much. So what else is worth talking about before I do a little demo? I guess talking about the resource thing, about kind of why this system works so well. The reason this works so well, and primarily, is because of mainly because of the fact it's two threads and not two processes, right? So for example, let's say you run the open system call, right? If it was the open system call, with the open system call, the way it works is you open a file and it returns a file descriptor. And the issue with running open in two processes is that the second process, if you run the open on process 2, obviously process 1 is not going to see that file. But with threads, if you run open on thread 2, thread 1 will be able to see that file, right? Because they share the exact same file descriptor table. So the key idea here is that basically if I'm able to make the system call here, in our worker thread, the trapping thread, the thread that's doing the system call hooking, will be able to see the results, which is why it's such a powerful primitive, right? Yeah. Before I do the demo, any like questions on like where I'm at? Like, yes, what's up? What's up, Adam? Huh? This is for a broader project. It's a reverse engineering, just sandbox. So I mean, this is other code that I wrote. This is for hooking. So basically, there's a thing called play integrity in Android. It's a very, very hard to reverse engineer tool. It's very, very hard to reverse engineer shared library. It's basically used for attestation and making sure that your Android is not rooted or or basically compromised in any way. So the point of this and this broad project is to basically look at that and basically build a sandbox which I can run that and then see exactly what the program is doing. Because the actual code, I'm gonna open it up real quick. The actual code is damn near impossible to reverse engineer. If I open a binary inject, I'm just gonna show it. There we go, it's libdroidguard. So as you can see, let's see if I can find an example. That's like really stupid. Yeah, most of it just like fails to disassemble most of it because it's so big. It's a good example. It just like blows up most of the time. That's not too bad. It's like a bad example. I'm not finding anything that's like terrible. It's like shit like this. Like this is like impossible to read. There's like some really bad ones in here though. Nah, it's not too bad. Most of these are just like. Yeah, I gotta build a big one. This is really silly. Yeah, so as you can see, like 101 arguments. Like there's like no way. Like what is this nonsense? Like who made this? So the point is, there's like no way I'm gonna sit here and reverse engineer this shit myself. So basically, the principle is that because it's meant for attestation, the idea is that it needs to be interacting with the system in some way, right? It needs to be looking at system resources to look for, because it wants to find compromise, it needs to look at system resources, look at things that potentially could be compromised, right? And to look at system resources, the only way to do that is system call hooking, right? And this is obfuscated as shit and back. So the presumption is that there's probably some anti-ptrace stuff in here, obviously, right? So that's kind of the principle. Invent something new to try to trick this and do a better job than this. Yeah, and there's also like other stuff here. This is basically Frida, but like in C++. It's much harder to detect because you're not working with like glib and stuff. It's like elf parsing. There's all kinds of stuff that I do here. But this is the system call hooking stuff. What Frida stuff do I do? It's not exact. Basically what it does is it allows you to hook. Because you know Frida Java, how it like hooks Java stuff. This is like that, but like in C++. So I basically just do what Frida does, but in C++ instead. The reason is because I can strip the symbols, because you can't really do that in C++. It's easy to detect Frida. It's not easy to detect this because there's no strings. Yeah. And I just have more control over this because I made the code, so I can tailor it much more easily to my needs and my and like whatever anti-debug stuff it's doing. So. It's much harder to detect. Because it's in process. I haven't tried this yet. I haven't tried it against it yet just because I haven't had the time to. But I don't think it would because it's just novel. Yeah. No. I had. No, I'm not gonna talk about that. Okay. Let's talk about. Okay, let me do a demo real quick. Yeah, let me do a demo. ADB shell. Please. The BTS phone. God damn it. What the fuck? Give me a second. Where is it? That's Python. Okay. So where is it? Okay, let's do just run this. LD library, was it LD library path, I think? exactly am I trying to? Wait 1 second. Okay. Yeah. Sorry, what was the question, Thanos? Well, I mean, it's just attestation. Attestation based. So there's certain apps that don't want your phone to be rooted for whatever purposes, because if your phone's rooted, that would allow you to reverse engineer their app or potentially do some kind of botting. So Play Integrity provides that service, and it's like, okay, here's some attestation stuff. Just basically saying, okay, can I attest that the phone is not rooted? That's it. That's like, and the way, if you can bypass that, and basically if you can generate valid Play Integrity tokens, basically, you can then perform a lot of really fun stuff. Yes, what's up? Phone to be rooted. Phone to be rooted literally means you just run root on the phone, right? Like it, like you saw that here, right? Like I am root right now, right? And I would not be able to do this if the phone was not rooted, right? Among other things, right? Like you can do stuff, run stuff like Magisk. You can run stuff like there's all kinds of fun Android stuff you can do with a rooted phone. Yeah. Yeah. So I guess what I do here, this is all like the Java stuff. Don't worry about that. In this case, I hook 2 system calls. I hook 172 and 63. I don't remember what those are anymore. Let's look that up. 172 is get PID, and then I hook 63, which is, I believe, read. So hook read and get PID. So I run get PID here before we hook everything. What does init do? I don't remember what init does anymore. Does init just like, when it just sets the trap handler? So yeah, I hook install, and then what? Oh, I like deleted the old code here. But there was old code here. I don't know. I don't know where that code went anymore. But there was old code here that basically ran read and ran get PID. So in this case, it hit trap for 172, which is get PID, and then it successfully was able to run get PID. So basically, this is just a demonstration that it actually works, and it's actually able to, 1, observe the system calls, and 2, actually successfully perform the system calls and return the result properly back to the original thread. The lamao, it was reading this flag, which has a content of lamao. So yeah. The other kind of nice primitive about this is that you can also be able to modify system call arguments very easily, because you have control, because you're the one making the system call now. So you have that window of opportunity to change. Yeah, what's up? Where I hook read? I don't hook read technically anywhere. I hook it here, technically. That's the hook code. Actually, that's all right. This is the hook code right here. I don't replace read with anything. You did miss this part of the presentation, Adam, so I guess I'll briefly go over it. So there's Seccomp BPF, which basically allows us to insert a program and run something. So basically, whenever you make a system call, you basically do seccomp. And what time is it, real quick? I got time. So yeah. So there's a thing called seccomp in Linux, and whenever it makes a system call, it basically runs a seccomp program. And that seccomp program is basically made up of what's called BPF. BPF is basically an assembly language in the kernel, and basically you can do kinds of things with that seccomp program. Now, the action that it takes based on the seccomp program is dependent on what the seccomp program returns, right? You have a bunch of return options. The 2 ones we focus on are allow and ret trap. Allow just allows the system call to occur. Ret trap just traps it. We'll talk about what trap means in this case. So in this case, basically what it's doing is it's basically grabbing the system call number. It's comparing whether that system call number is one of the system call numbers we want to hook. If it is, then you jump to ret trap. What's up? Yeah, I mean, not really. Yeah, the Zyjust guy was Top John Woo, I think is the guy who does it. He got rid of. He just got tired of it playing that mouse game. There's someone else who does it now. I forget. It's like I forget who it is now, but there's Magis modules out there to bypass play integrity. Play integrity is getting worse these days because a lot of people are moving to strong, which is really dependent on trust zone, because most Android apps have a trust zone. Most Android phones have a trust zone these days, so it's running in trust zone. So in that case, with strong integrity, you're kind of fucked unless you have a trust zone exploit, which is hard. So yeah. Anyway, back to your question, Adam. So you got seccomp so ret trap, what it does if it does return ret trap, in this case it's one of the system calls for hooking, it basically sends a signal, a SIG-sys signal. That SIG-sys signal is right here, and then it basically hits this trap handler, and this is where we actually hook our system call right here. Yeah, that gives us an opportunity to hook a system call. There's a bunch of other tech. If you want, we can talk about it a little later. But yeah. Yeah, I mean, that's kind of it. That's kind of what I want to show. It works. It's kind of cool. It's not done yet, but the proof of concept is done, and it works. All right, cool. Thanks for listening.